Welcome. We're going to be doing Physics 123, lab number 2. This is resonant standing waves in a wire. And so we're going to be vibrating this wire and examining when we get resonance at a particular frequency of vibration as well as a particular tension on the wire. And we're going to be doing 2 trials of that in order to our ultimate goal, besides obviously understanding resonance, is to be able to measure the linear mass density of this wire. So mass per unit length is what we're after. So thanks for watching and enjoy the lab. Okay, let's begin by introducing some equipment here. So what we're going to be doing to power this is by using a sine wave generator and a string vibrator. And so when we connect these, we can change the frequency, right? We're just going to set it at 60 hertz for this lab, but this will input a sine wave into this generator, and so it's going to be this this platform is going to be vibrating at a frequency of 60 hertz sinusoidally. And so it's just like if you could model the up and down motion, it would look like a sine wave with a frequency of 60 hertz. And so we can see that we just have, I might take this off for now. We can see that we just have a plain wire here. It's just a thin wire. It's a little bit hard to see, but it's pretty strong wire and it vibrates quite nicely. And it's just overlaid over the table. We have the white underneath so it's easier to see the oscillations. And then this is just connected to a pulley so that the length of the wire adjusts with the tension. So this is always nice and a good tension, and the tension is based on the weight hanging from this cup. And so we have a squeeze bulb where we can take some water and then we can squeeze it back out, so we can adjust how much water is in the cup here, and by how much weight from the water is in the cup, we have a different tension on the string. And so based on the tension on the wire, it's going to vibrate at different modes, at different frequencies. It'll have different resonance frequencies. And we have a meter stick to go ahead and just measure the length of the nodes, as well as a digital scale where we can unclip this bucket of water and then weigh how much it is in order to ascertain the tension in the string based on mass times gravity. And that's all the equipment here. Okay, so we're going to start by trying to find the first resonance frequency that we can get given the apparatus setup. And so right now you can see that it's not really in resonance. The thing is still vibrating at 60 hertz, but the tension isn't such that we don't have these nice reflections from the waves which will cause resonance. And so in order to try to get resonance, I got some water in this dropper. I'm going to come in here and just slowly add it. I'm just going to slowly add it until we start to see nodes form in the wire. Okay, that's pretty good right there. So we saw it for a second, right? We can definitely see the nodes and the antinodes. We're just going to I'm going to add a little bit more to try to get it stable. I need a little bit more. Oh, actually that looks pretty good. Okay, let's see if it's stable. It looks pretty good. Alright, so here we have 1, 2, 3, 4, 5 nodes. And so what we want to do is try to measure the wavelength of the standing waves here. And so remember, the wavelength is going to go up and down, so the distance of 2 nodes is going to be the full wavelength. And so what we're going to do is we're just going to come in here and put our ruler underneath. It doesn't really matter which nodes we're looking at. Maybe we'll come down here and zero it at the node down here. Okay. And if we go right over the top, we can see that's pretty zeroed, trying to reduce parallax. Alright, we'll go with that. So we're starting here, and then we're going to go over, there's 1 node there. Again, we want the full wavelength though, so we're going to go 1 more node and measure here. And so let me try to adjust, make sure that we're still zeroed. Okay, so we're still at the 0 at the other end, and that's the measurement you want to make. So it's about 59.6 or 7, maybe 6. I don't know, you can make your own measurement based on what you think. but that's for 5 nodes, and the wavelength is what we just measured there. And so what we're going to do is we're just going to turn off the vibrations real quick, and then detach our water bucket. We have our digital scale here. It's in grams, and it's zeroed right now. So if we just add that, the weight of the bucket combined with the water is 77.0 grams. So write that down along with the wavelength. And based on that and the calculations you did at the beginning of the lab, you should be able to come up with the linear mass density of the string. Okay, now that we got that data for 5 nodes, we're going to add some water to increase the tension, and then look for another resonance frequency with less nodes. So I just got my squeeze bulb, and I'm putting wire at the end. So looks like there's one, or close to one, that's 4 nodes. Since we already got 5, I'm gonna go ahead and try to get maybe 3, so we can have some variety here. So we can see that when it's not at one of these resonant tensions, we see some vibration, right? But it's nowhere near the amplitude of the vibration at resonance. And so one thing to think about is why does this only occur for certain weights, for certain tensions in the wire? Okay, looks like we're getting close to the third, well, the 3 nodes. Well, I guess it'd be 3 antinodes and 2 nodes in the center. Okay. And it looks pretty good. So, we can definitely see it's oscillating with a lot more amplitude. You can even hear it in the video. We see our 2 defined nodes here. And we want to measure another wavelength, which is from 1 node, 2 nodes over. And so we'll take the meter stick and put it. You can see that there's actually some side-to-side vibrations, which if I put my finger there, maybe it gives us a little sharper node there. But that's what we want to measure from. So I have that centered, and then if we go, oops, I knocked the, okay, that's better. When we go 1 over, we're at about 50, okay? A little bit less than 50, and we can actually just measure all the way to the end, which is going to be a distance of 2 antinodes and 2 nodes over. And so right at the top here is where the node stops vibrating, or where the node is. And so at the top of the pulley, measure where that is on the meter stick, and then that's your wavelength for this second trial. Plug it, and then measure the weight that we had to get that. Then this you can find the tension. So we put on our scale. We've got 224.3 grams. And so this should be all the data that you need to find the linear mass density again using this trial. They should be pretty similar, but that again is the end of the data collection. Okay, so go ahead and use those data that you just collected to fill out your student sheet. If you do get stuck though, you can go ahead and finish watching the video where I will include a couple hints that may help you if you get stuck. The first thing that you want to do, and it explains this in the lab sheet, so I'd go back and reference it if you are stuck, but the first thing that you want to do is you want to find the velocity of the waves at the particular resonance frequency that we were measuring. And so if you look here, the velocity is given, well, first we want to find velocity from the frequency and the wavelength, right? And so if you remember, frequency times wavelength is the speed of the waves. And so we should have measured the wavelength, and the frequency was 60 hertz because that's what we set our sine wave generator to be. So once you have that, you can get the velocity, and then you would also want to find the tension. Pretty straightforward, just using the mass and the acceleration due to gravity. You find the tension, and then you use this relation that it gives you here, V equals square root of T over mu, to solve for the linear mass density. So pretty straightforward, but if you do get stuck, don't be afraid to reach out to a TA for help. Thanks.